Hello, welcome to our lecture on simple harmonic motion. I just realized I hadn't pulled up my notes yet, so I'm going to do that. But basically, simple harmonic motion is just what happens when you have either you can either define it as u is proportional to x squared, where x is whatever your displacement vector or displacement variable is. Or you can have the definition be that d squared x dt squared is proportional to negative x. So, of course, the example that we've already seen of this type of equation is the uh, simple spring where ma equals negative kx, or A is equal to negative K over mx. So what we don't know is uh, immediately is what type of motion it's going to incur, what type of motion this looks like, where the acceleration is going to be non-linear. It's not going to be the same acceleration at any given time, because as you get farther out, you have more acceleration pulling you back, and as you get farther in, you have less acceleration pulling you back. So, what does this function look like? Well, if you know anything about differential equations or anything like about taking derivatives, you can make the guess that x of t is going to be equal to a times cosine omega t plus phi, where omega equals 2 pi over the period, which is equal to 2 pi times the frequency of the wave, or of the cosine wave, yeah. And then phi is just to tell us how far along in the cycle this cosine is when uh, um, when t equals 0. So, for example, we have this wave of x versus t, and at this point, um, t equals 0. So this has a value of a cosine of phi. So this phi is called the phase shift, and it tells you how far along in your uh yeah, how far along in your cosine wave you are at t equals 0. So x of t is equal to cosine omega t plus phi, and then that means that v of t is going to be negative a sine omega t plus phi times omega, because the derivative of a cosine is negative sine. And then uh, this amplitude tells us the maximum value of x of t, because a times cosine omega t can never be higher than a. So this is also going to give us our Vmax times sine omega t plus phi. So negative Vmax sine omega t plus phi, because uh like the x of t, like the cosine sine has maximum value of 1, so the maximum value of uh the velocity is equal to a times omega. And then you also have A of t equals negative A times omega squared cosine omega t plus phi is equal to negative omega squared times x is equal to negative A max uh, cosine omega t plus phi, where A max is equal to A omega squared. So when we plug this in, let me just save this really quick. But when we plug this in, I tried to get an eraser. When we plug this into our equation where uh, M A equals negative kx, then A is equal to negative k over m times x is equal to negative omega squared times x. So omega squared is equal to k over m. And that's going to be the interesting thing about this, where uh, no matter what amplitude you pull the uh, no matter what amplitude you pull the spring at, its angular frequency, 2 pi f, is going to be constant just based on the mass of the object that's moving and the spring constant of the object or of the spring. So, yeah, that's the most basic form of simple harmonic motion. It's called simple because it is just going back and forth harmonically. And it's just a cosine times omega t plus phi times a. So it's really as simple as we're going to get this for this lecture, but it is basically everything you need to know. So us, uh, there was earlier I said something about it being the displacement vector or the displacement variable that you were talking about. So why I said that is because springs are not the only materials that or the only objects that undergo simple harmonic motion. You can also find simple harmonic motion in a pendulum undergoing a torque due to gravity. So mg is the force, and then the angle between the displacement vector L, or the displacement vector from the pivot point up here, and mg is going to be theta as well, because both of them are making an angle with respect to the negative y-axis. So this vector is also mg. Uh, this mg vector, this weight vector, is going to be at an angle of 30 degree or of theta degrees, sorry. With respect to the vector that you have for the rotation. So what this means is that torque equals I alpha is equal to R F sine theta is equal to L times L times mg sine theta, where L is the distance to the center of mass, Uh, M is the mass of the pendulum, and I is the moment of inertia of the pendulum. So we can say we can define a simple pendulum as basically just being a massless rope with a big mass at the end, which is what we see for grandfather clocks. Or we can derive it. Oh, and then I wrote alpha omega instead of alpha, which is a big problem. I alpha equals L times mg sine theta. Uh, so we can write a simple pendulum as just being like grandfather clock's pendulum, where there's just a big mass at the end of thin stick. Or we can define alpha. Oh, and it's negative RF sine theta because it's going to be pointing in the direction that restores uh, motion back to its original starting point. If you do the right-hand roll, you'll see that. So alpha equals d squared theta dt squared is equal to negative L mg over I times sine theta, which is approximately equal to negative L mg over I times theta, which is called the small angle approximation. Small angle approximation, and it's good within 1% up to about 15 degrees. And then notice that instead of being in degrees, this small angle approximation is in radians. Uh, which basically, if you do any sort of calculus with your angles, you have to use radians instead of degrees because it's going to degrees don't really physically mean anything. That's just how we split up the circle, but radians correspond to the physical values like R times omega equals V, where V omega is in radians per second under 15 degrees. So alpha, so theta of t is going to be equal to uh, A cosine omega t plus phi, again, because we have this same uh, form of, we have the same form for the differential equation that we're looking at, but omega is in this case negative L mg over I, or for the case of a simple pendulum where I equals ml squared, where it's just a point mass at the end of the uh it's just a point mass at the end of the uh material at the end of the swinging rod. Omega this goes to omega equals negative L M G, or sorry, that shouldn't be, it should be omega squared equals that, and there shouldn't be a negative value there. square root of lmg over I. And then this is going to become lmg over ml squared, which is just going to be equal to g over L. So this is for a simple pendulum. This is a more complicated version that includes the moment of inertia is called the physical pendulum. And then this is just going to act in the same way that the spring does, except instead of x varying, the angle varies. So that's the case. And then we're going to go over one more type of pendulum or simple harmonic motion before moving on to our next section, which is going to be torsion pendulum, where you have something hanging from a string, and then you twist the string in such a way that it tries to get back to its original place. So if you've ever played with a string, if you've ever done any like if you played with the string, if you played with your headphones or the strings that we use in the lab, then when you twist them, they try to twist back to their initial position. So that is called torsion, and it has uh the form of torque equals negative kappa theta, where I d squared theta dt squared is equal to negative kappa theta. So d squared theta dt squared is equal to negative kappa over I theta. So this is simple harmonic motion with omega equals square root of k kappa over I. So yeah, that's simple enough. It's just another type of pendulum that we're talking about. But this is what simple harmonic motion is, and it's really useful if you start getting into physics because, as we'll go into more in the next section, this simple harmonic motion can approximate basically any motion in the world to uh, uh, early degree, to a degree where if you don't change x too much, then basically any uh any equation or any physical energy that relies on that's going to have restoring force is going to behave simply harmonically up until a point. So, yeah, thanks for listening. I'll move on right now.